Okay, based on the way this question is phrased, I'm thinking that you want to see an evaluation of this definite integral using the limit as n approaches infinity of a Riemann sum. Okay, so it turns out the area under this curve from 0 to 4 is 44 thirds, or 14.666 repeating. Okay, you'll see on the next boards where these expressions come from, but you can see that they're getting pretty close to this 14.66 as n gets really large. Here n is 1,000. So what is all this stuff? Okay, this 4 over n is the width of a typical subinterval. So from 0 to 4 has a width of 4, and we're going to divide that into n equal subintervals. So the width of one of these is 4 over n. Okay, and we're using right-hand endpoints here, which means we want the x-coordinates of these points right here, and we want to plug them into the function. So if we start at 0 and move one width to the right, the x-coordinate of this point is 4 over n. If we move to this point, it'll be 0 plus 2 of those. And if we have generalize the ith x sub I, it's going to be I times 4 over n, or 4i over n. Okay, so let's see what happens on the next board. Here's the calculation of the width. X sub I is 0 plus 1 width. That's the first right-hand endpoint. X sub 2 is the second right-hand endpoint. 2 times 4 over n. An expression for the ith x-coordinate is 0 plus I times the width, or I over 4n. And this expression is what we're going to plug into the function to get a formula to help us get a formula for the area of the ith rectangle. So here we have plugged in 4i over n into the function 9 minus x squared. So this expression right here is the height of the rectangle, and this 4 over n is the width. And if we let I go from 1 to n and add up all those areas, we'll get an approximation for the area. But if we let the n approach infinity, we'll have hopefully an expression for the exact area. Okay, so if we square this 4i over n and then distribute the 4 over n, this is what we get. And from here, we're using summation formulas. Okay, so this sum right here can be broken apart into the sum from I equals 1 to n of 36 over n minus that. Okay, and 36, and remember, 36 and n are just constants. So I can move the 36 over n out front. I can move the 64 over n cubed out front of the summation symbol. This expression right here, if I add up n ones, the value is just n times 1, which is n. And 36 over n times n, these n's cancel out. The limit as n approaches infinity is just 36. But here we've got something more interesting. What's the formula for the sum of I equals 1 to n of I squared? Well, it's this. Where does that come from? Quickly go to board 3. There's where it comes from. It's a well-known formula for the sum of I squared. So you can prove it with mathematical induction. Okay, so like if we said the sum from I equals 1 to 5 of I squared, we have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. If we added them all together, we could get that result by plugging 5 into this formula. Okay, so that's where that comes from. And now, if we multiply these factors together, Move the 6, 64, 6 reduces to 32 thirds. Divide n cubed into each term of this polynomial up here. We get something that looks like this. And now here's the key: as n approaches infinity, these terms approach 0. And this term approaches 2, because the n cubes cancel out. 2 times 32 thirds is 64 thirds. 36 minus 64 thirds is 44 thirds. So there's how you would calculate the exact area using the definition or the limit as n approaches infinity of a Riemann sum. Hopefully that's what you were looking for. If you have any questions, post a comment.